I'm Terrell Ibanez, and this is generating roller coaster tracks as a motion planning search problem for CS221 or RCTMotion. So roller coasters are an interesting version of the motion planning problem, whereas real world constraints like financial cost do apply, but instead of the shortest or most efficient path, a coaster should really be taking the most efficient path where you're trying to go from say point A to point B. A coaster should be taking the scenic route, so to speak. But however, unlike a path winding through a park where we could just consider the scenic route as being scenic by the surrounding scenery, the trees, and the various stationary objects, the interestingness of the path itself is what matters. The changes in the turns and the variety in the g-forces that are from changing direction, right? And so the way it's modeled is a-star search with the motion planning, wherein the coaster car is treated as an agent that has a set of available actions at any given time, and those actions are the track pieces, like a left turn, a right turn, go up, go down, etc. Begin sloper, and you can actually see those here when I'm generating the possible tracks, and this is implemented as a as state transitions where you can only make certain kind of transitions where like you can't immediately begin to go up if you're already in a right bank roll turn, etc. And what's interesting is that when you consider that the state of the coaster car, it's either going up or going down, or it's making a bank turn, and its physical position at any given time, if you keep making transitions from that state to new states where you simulate a left turn or a right turn, and then that's the new state of the coaster car, eventually if you get the coaster car to the end of the station, then you'll get a sequence of tracks which actually make up the coaster, if that makes sense. Perhaps it's easier if I demonstrate that a little bit, but we'll get to that in a second. Or actually, it is kind of take a while to do that search. So let me start that right now. Code. And so the way that this works is that given these states and these tracks, we perform an A-star search where it's trying to minimize the cost of building the roller coaster. And for costs, I've actually done two approaches, where one is using constant costs, where each one just costs $1, and also like realistic financial costs, or well, not really realistic, but using the costs from the game. In this case, OpenRCT2, where a certain track piece might cost like $30 or so. I'm not sure if the ones in the track designer have costs. Yeah, you don't see that, but in the full game, you do have that. So while we wait for these track search to complete, searching a lot of track states. One of the things that we do to make it to make this kind of easier is that every roller coaster track, needs a station and a lift hill. So we begin the state by the search by actually giving that to the coaster up front, to the algorithm up front, and simulate the state going through the track and then up through the lift hill, so that it will begin at the state at the top of the lift hill, right? And then from there, it'll do the search and then try to get to the end of the station, where it'll come here and then go all the way down to the bottom of the station. Right? And it is still searching. Yeah, this takes a while. As for the heuristic that I use for the A-star search, I use Manhattan distance in this case, which is if you treat the 3D space as a grid, then it's just X, Y, and Z, the coordinates kind of differences added together if you were to move in only straight lines, right? And then this is then multiplied against the cost of a single track piece, like a single movement grid's track piece. So like say if I were to add like that track piece, and that's just kind of abstracted out as cost, or as the heuristic for cost. See, this is still searching, taking its sweet time. Oh, I see. It's because I'm recording, which is using up a lot of CPU, so it's actually taking time away from the search algorithm. So this might take longer. I might have to record this video again using by running this first and then beginning to talk. But we'll see if this finishes soon enough, because this usually runs within a minute or two. Ah, there we go. And because it takes too long to actually build out the track, you can see the individual pieces are given to you. But in the meantime, I can show you the visualization of the 3D colliders that are used to prevent inertial track, the individual track collisions when building the tracks out. It was a huge problem when I first started out that they would intersect with each other. And so I ended up having to implement a volumetric track collision system where I represent 3D points around generated track pieces as a set, so that when I add a new track piece, I can test against insertion to the set. And if those points already exist, then there's a collision, and then we know that we cannot use that track piece. But I'm well over time now, so thank you, and I hope you enjoyed it. There are some pictures of the generated tracks in the report. You can find those in there.